how the unbearable difficulty of communication might relate to ontology. Physical physics has ended up to a state of stagnation. The ideas that emerged after the establishment of the standard model have led nowhere. On the other hand, since the background noise in particle physics experiments is huge, one must precisely know what one is searching for. New theoretical ideas and theories are needed, since the testing of dead ideas is a waste of time. Regrettably, the communication of new ideas has become extremely difficult. What could be the reason for the situation? The brief possible answer is ontology, or rather lack of it. In the sequel, I try to explain what I mean with this. The development of quantum theory raised the question how to test the predictions of the theory. It turned out that the outcomes of the quantum measurements were not predictable, and only the probabilities for outcomes in the measurement of the selected commuting observables were possible to predict. This was in a sharp conflict with the determinism of Schrödinger equation, and also with the classical determinism. Einstein, who had constructed general relativity, could not accept this, since it would have made his theory pointless. This led to the Einstein-Bohr debate. The classical predictions of general relativity have been repeatedly verified, as also the predictions of quantum theory. Both sides were winners and losers in the battle. Numerous interpretations trying to circumvent the paradox of quantum measurement theory emerged, and Copenhagenian interpretation became the textbook interpretation. It gave up the notion of ontology altogether. No reality actually exists as in mathematical sense, and quantum mechanics is only a collection of computational recipes to predict the probabilities for outcomes of quantum experiments. In particular, the notions of quantum states and wave function are not anything real and must be given up as descriptions of something real. This led to a kind of postmodernism. Anything goes. Inflation theory and superstring models represent the extreme in this sense. In the basic version of the superstring model, the four-dimensional spacetime is replaced by two-dimensional string word sheets in 10-dimensional target space, and four-dimensional spacetime is believed to emerge in a mysterious process known as spontaneous compactification. So-called landscape catastrophe emerged as an outcome of spontaneous compactification and meant a complete loss of predictivity. But even this is not seen as a problem if one gives up ontology altogether. The outcome is indeed postmodernism. There is no grand narrative, and science reduces to science fiction literature. The TGD approach takes ontology seriously. It takes it as a starting point, and it is therefore a diametric opposite of the prevailing Copenhagenian approach. In the TGD universe, there are two existences, physical and subjective. Physical existence reduces to mathematical existence, and theory of subjective existence, theory of consciousness, to a suitably generalized quantum measurement theory, which is free of this basic paradox. The conditions of mathematical existence are extremely powerful in the infinite dimensional context. Number theoretic and geometric visions as duals of each other fix TGD uniquely. Also, the consistency with the standard model symmetries leads to the same outcome. Ontology of TGD at the classical level. TGD emerged as a solution to an ontological problem. The notions of energy, momentum, and angular momentum are not well defined in general relativity. Already Emmy Noether realized this, but her discovery was put under the rug. My own discovery was that the hybrid of general and special relativities obtained by fusing the postulates of general relativity, namely general coordinate invariance and equivalence principle, with the relativity principle or special relativity, one ends up to a theory in which conservation laws are not lost. The prediction is that spacetime at the fundamental level is not an abstract four-geometry, but corresponds to a four-dimensional surface. In some space, which is Cartesian product of Minkowski space, and some compact space with a small size. By choosing this small space to be CP2, complex projective space, one obtains standard model symmetries and classical fields. They are geometrized, so that TGD is unique. Einsteinian spacetime with four-dimensional Minkowski space projection emerges at the quantum field theory limit at long-length scales. The new ontology, which I call zero-energy ontology, ZEO briefly, identifies spacetime as four-dimensional surfaces, and it has dramatic implications in all scales, in particular cosmology and astrophysics. There is also a connection with string models. Spacetime surfaces can be seen as orbits of three-dimensional surfaces representing particles, replacing the strings and point-like particles. In fact, the conformal invariance of string models extends to a four-dimensional symmetry. And this symmetry implies that spacetime surfaces are minimal surfaces, with lower dimensional singularities giving rise to vertices. TGD strongly suggests also other infinite-dimensional symmetries, as isometries of this world of classical worlds consisting of these spacetime surfaces. If three-dimensional surfaces are identified as particle, the minimal surface property generalizes wave-particle duality of massless particles. Minimal surface generalizes light-like geodesic, and minimal surface equations are nothing but nonlinear geometrized variant of massless field equations. This means geometrization of wave-particle duality. Twist realization of TGD involves one more ontological miracle. Twist realization has shown its power in the construction of supersymmetric quantum field theories. And the natural question is whether the twist lift of TGD is possible, using as a basic recipe the induction of classical fields, which is used to achieve the geometrization of the gauge fields of the standard model. One must start from the 12-dimensional product of the twistor spaces of Minkowski space and CP2. A good candidate for the twistor space of the spacetime surface is a six-dimensional surface which has a structure of sphere bundle having spacetime surface as the base space. Could one obtain also this six-dimensional surface as a six-dimensional analog of Bohr orbit for some action? This is a question. This turns out to be possible, and a dimensional reduction leads to a four-dimensional action, which is scalar action as an analog of Maxwell action, plus a volume action having an interpretation in terms of cosmological constant, which depends on periodic length scale and approaches to zero in long length scales. This solves the problem posed by the gigantic value of the estimate for a cosmological constant in standard theories. This is possible if the twistor spaces in question allow Kähler structure. This is possible, but only for Minkowski space and CP2. TGD and physics would be unique. The basic goal of the quantum TGD is to construct scattering amplitudes. The first guess was that scattering amplitudes are defined in terms of a path integral over all four surfaces. Rather conservative guess. However, field theories have an ontological problem. The path integral does not exist in a mathematical sense. In TGD, this problem is magnified since any general coordinate invariant action is extremely nonlinear, and there is no hope of the elimination of divergences by renormalization. Therefore, the realization of path integral as integral over four-dimensional surfaces connecting initial and final three-dimensional surfaces makes no sense mathematically. The solution of the problem is simple. General coordinate invariance is realized by holography. By assigning to a given free surface a unique or almost unique four-dimensional surface, analogous to Bohr orbit. Path integral disappears and is replaced by a sum over these four-dimensional Bohr orbits, finite in number perhaps. So, instead of three-dimensional surfaces, the four-dimensional Bohr orbits are basic dynamical objects. And quantum TGD reduces to wave mechanics in the space of these Bohr orbits. World of classical worlds, as I have used to call it. The world of classical worlds must exist mathematically, and it must allow Kähler geometry, otherwise the geometrization of quantum theory is not possible. There is again an ontological problem to be solved. Dan Fried studied loop spaces and found that the Kähler geometry exists and is unique. There are excellent reasons to expect that the same is true in TGD, simply because the dimension is higher than 2 now, and situation is even more demanding. Momentum position duality plays a key role in wave mechanics and should also generalize. The natural momentum space counterpart of embedding space is 8-dimensional Minkowski space as its cotangent space. This 8-dimensional Minkowski space and embedding space should provide complementary descriptions of physics. I call this M8H duality. Here emerges a new ontological element, number theory. It has no fundamental role in standard physics. It took some time to realize that this 8-dimensional space can be interpreted as octonions, since the real part of octonion squared gives the Minkowskian norm. Dynamics in this octonion space, Minkowski space, can be formulated as a condition that the normal space of the four-dimensional surface is quaternionic. That is associative. Associativity becomes a number theoretical variational principle. M8H duality maps these four surfaces to embedding space, provided the normal spaces contain an integral distribution of commutative subspaces. The normal space of four-dimensional surface is parameterized by a point of CP2, and this leads to M8H duality. This duality has an interpretation also as a physical counterpart of Lagrange duality. Classical number fields, real and complex numbers, quaternions and octonions become parts of the ontology. Number theoretic vision in turn leads naturally to a hierarchy of periodic number fields and others, and also to the algebraic extensions, extending the ontology of the standard physics. A natural assumption is that the spacetime surfaces are characterized as roots of two polynomials. They are functions of the four generalized complex coordinates of embedding space. If the coefficients of the polynomials are in an extension of rationals, call it E, one obtains number-theoretic evolution as a hierarchy of these extensions. The polynomials defining space-time surface as a section of the six-dimensional twistor surface play a key role in the understanding of periodic primes assigned to elementary particles as ramified primes. The extensions of rationals and the extensions defined by the roots of polynomials P define evolutionary hierarchies. The dimension of E serves as a measure for algebraic complexity and as a kind of intelligence quotient, and defines an effective Planck constant. And the larger its value, the longer the scale of quantum coherence. This is something totally new. The phases of ordinary matter with a non-standard value of effective Planck constant behave like dark matter. They do not correspond to a galactic dark matter, but to missing baryonic matter, whose portion has been increasing during the cosmological evolution. Galactic dark matter is assigned to cosmic strings and monopole flux tubes as a dark energy. Again, new ontology solves a physics mystery, two mysteries. The ramified primes assigned to the polynomials as divisors of its discriminant have physical interpretation. They correspond to periodic primes characterizing periodic mass scales and length scales too. Number-theoretic physics, periodic physics, analytic physics can be regarded as physics of cognition. The common points of real and periodic space-time surfaces consist of algebraic numbers in the intersection of the extensions of polynomials involved, and they define universal discretization, providing a cognitive representation. Correlates of cognition as points common to the sensory world and cognitive world, they become a part of the ontology. The counterparts of Schrödinger amplitudes are identified as superpositions of four-dimensional Bohr orbits. That is, spinor fields in the world of classical worlds, WCW. This requires that the world of classical worlds has spinor structure. The gamma matrices are needed and are identifiable as super counterparts of the infinitesimal generators of isometries of world of classical worlds. They are in turn identifiable as neutral charges, defined at space-time level. The gamma matrices are identifiable in terms of oscillator operators of free second quantized spinor fields of embedding space. This makes it possible to calculate fermionic correlation functions, which is certainly a fundamental task. Free spinor fields of embedding space define the fundamental fields, and bosons can be regarded as bound states of fundamental forms, fermions. There are no fundamental boson fields. This is important. This, however, creates an ontological problem. Fermion and antifermion numbers would be separately conserved. In reality, only their sum is conserved. The idea is suggested by class standard quantum field theory. One can calculate scattering amplitudes for fermion per emission in classical fields. This is approximation, but now it would become exact. The classical fields would be induced, that is, geometrized gates and gravitational fields. It turns out that fermion pair creation is possible only in dimension d equal to 4. This is due to the fact that in the four-dimensional case there exists an infinite number of exotic smooth structures. They differ from the standard smooth structures by lower dimensional defects, identifiable as singularities defining vertices, so that a deep connection between four-dimensional geometry and quantum field theory emerges. In general relativity, the existence of the exotic smooth structures is lethal. Ontology shows again its marvelous power. A realistic quantum theory allowing pair creation is possible only in a dimension d equal to 4. Solution to the basic problem of quantum measurement theory. It was quantum measurement theory which led to Copenhagen interpretation, which is one cause for recent stagnation of theoretical physics. Could TGD solve the problem? The spinor fields of classical worlds, the space of four-dimensional Bohr orbits, define the counterparts of wave functions in TGD. Quantum jumps occur between them. The non-determinism of quantum jump conforms with the classical determinism of the Bohr orbit. The superposition of Bohr orbits is replaced by a new one. Nothing happens to the Bohr orbit. The basic problem of quantum measurement theory simply disappears in zero-energy ontology. The basic implication is that there are two times: the geometric time, identified as time coordinate of Minkowski's pair, or time coordinates of the space-time surface, and subjective time, experienced time, identifiable as a sequence of state function reductions defining self. These are not identical, although they must be strongly correlated. One must generalize the quantum measurement theory. The outcome is a quantum theory of consciousness. It brings the observer part of the ontology as a conscious entity, self. In standard quantum theory, one has two kinds of state function reductions: the ordinary state function reduction and the sequences of repeated measurements of the same observables producing the same measurement outcome. Zeno effect is in question. In quantum optics, the latter measurements are replaced by weak measurements which affect the system slightly, and from these we must start. TGD predicts big state function reductions. They are counterparts of ordinary state function reductions, and also small state function reductions. They define the TGD counterpart of Zeno effect. The prediction is that the arrow geometric time changes in big state function reductions. This is something totally new. In small state function reductions, the state changes, but the arrow time is preserved. The sequence of state function reductions defines a conscious entity, self. And BSFR, big state function reduction, means the death of self, followed by reincarnation with an opposite arrow of geometric time. A more precise understanding of the relationship between the geometric time and subjective time requires the introduction of further ontology. Perceptive field characterizes a conscious entity, self. The perceptive field of the conscious entity is identified as a causal diamond, which is Cartesian product of causal diamond of Minkowski space with CP2. This small CD is a causal diamond of Minkowski space identified as the intersection of future and past directed light cones. Causal diamonds form a scale hierarchy of selves, conscious entities. One can apply Poincare transformations, special conformal transformations, and scalings of Minkowski space on these causal diamonds. The finite dimensional space of causal diamonds is obtained in this way and forms the spine of world of classical worlds. This in the sense that world of classical worlds decomposes to sub-VCVs, consisting of space-time surfaces inside a given CD. That is a fractal scaling hierarchy. In zero-energy ontology, fermionic parts of the states are superposition of products of fermionic Fock states at the opposite boundaries of CD. The size of causal diamond increases in statistical sense in the sequence of state function reductions, smaller state function reductions. They leave the members of the state pairs at the passive boundary invariant. It's no effect. It is restricted to the passive boundary only. But they change the state at the active boundary of causal diamond. Since each state SSFR is preceded by an analog of unitary time evolution. This change corresponds to conscious experience. The geometric time can be identified as a distance between the tips of the causal diamond, and it increases in statistical sense, since the unitary time evolution in question corresponds to a dispersion in the space of causal diamonds. And SSFR means a localization in this space, in this moduli space. There is a natural correlation between the subjective time measured using SSFR as a unit and geometric time identified in the proposed way. Still, one key idea about ontology must be mentioned. In the ontology of classical physics, one assumes the existence of a unique reality behind its mathematical description. The quantum Platonia of the spinor fields of world of classical worlds as mathematical objects is the counterpart of this reality. There is, however, no need to postulate anything behind it. The quantum sums of conscious entities hopping around quantum Platonia give rise to conscious information about this reality. Number theoretic evolution forces the increase of algebraic complexity and creates increasingly complex memory representations about the quantum Platonia. The quantum Platonia of TGD differs from that of Tegmark is that it is not a zombie, but teems with life. To summarize, the basic difference between the standard view of theoretical physics and TGD is that since TGD solves the quantum measurement paradox, it can accept ontology. Ontology has popped up again and again in the development of TGD and has led to a completely unexpected cascade of new deep ideas with strong predictive power, since a mere mathematical existence fixes physics. What comes to mind is Giordano Bruno. He dared to propose that the universe is full of solar systems like ours and life is everywhere. It had been realized already that Earth is not a center of cosmos, but the ideas of Bruno were simply too much. He was burned on the stake. My crime has been the non-Copenhagenian claim that something exists, and even worse, there are two kinds of existences, physical and subjective. I was not burned on stake, but learned that what it is to be an academic zombie.